Hello friends, this is Shefali Ghutke, currently working as an assistant professor in Civil Engineering Department at Tulsiramji Gaikwad-Patil College of Engineering and Technology, accredited with NAC A+ grade. So today I welcome you all in today's lecture, that is Geotechnical Engineering 1 lecture. In today's class we will going to discuss about permeability of a soil. So the soil permeability is defined as the capacity of a soil which allows the water to flow through it. That is the quantity of a water which is flowing for a unit of a soil surface under a pressure of 1 unit hydraulic gradient. As we know, when the soil particles are bound together, in that condition there is a space between the particles. This space is called as a voids. Okay, which gives passage to the water, that is flow from higher energy to the lower energy. Soils are generally permeable due to the existence of interconnected voids through which the water will flow from high point of energy to the point of low energy. As you can see in this picture, this is the pervious soil in which the water is flowing from higher energy level to the lower energy level, in which this HA is nothing but the total head at point A and this HB is nothing but the total head at point B. So we can calculate the head loss, which is equal to HA minus HB. Okay, so a soil is highly pervious when the water can flow through it easily. As example are the gravels. As you know, in gravels, the void space are very large, so the water can flow easily. And in impervious soil, the permeability is very less and water cannot easily flow through it. Example are clays. Okay, so the rock are impermeable in nature. The study of the flow of a water through the permeable soil media is important in soil mechanics. In geotechnical engineering, permeability of a soil plays a very important role. Now the importance of permeability. Why permeability is very important? Because the following application illustrate the importance of permeability of a soil in geotechnical design. Permeability influences the rate of a settlement of a saturated soil under the load. The design of an earth dam is very much based upon the permeability of a soil that is used, because in earthen dam is made up of a locally available material. So if the permeability is very more, in that condition there is a chances of a failure of a earthen dam. The stability of a slope and the retaining structures can be greatly affected by the permeability of the soil involved. The filters made of a soil are designed based upon their permeability. Basically, these following factors affects the permeability of a soil, which includes the particle size, void ratio of a soil, properties of a fluid, shape of a particles, structure of a soil mass, degree of saturation, adsorb water, if entrapped air and organic impurities in the water is present, when the temperature is rise or decrease, stratification of soil. Basically, the permeability is based upon these factors. So first we will see particle size, how particle size affects the permeability of a soil. The permeability varies approximately as the square of grain size. It depends upon the effective diameter of a grain size. Void ratio. Increases in the void ratio increases the area available for the flow, hence the permeability increases for the critical condition. It means we can say that the permeability is directly proportional to the void ratio, because if the void ratio is increased, in that condition the permeability will increase. It means the water can easily flow from higher energy to the lower energy, because there is a much larger space for water to flow. After that, the properties of a pore fluid. Pore fluids are the fluid that occupy the pore spaces in a soil or rock. Permeability is directly proportional to the unit weight of a pore fluid and inversely proportional to the viscosity of a pore fluid. If the viscosity of a fluid is more, in that condition, the permeability will be very less. Okay, viscous fluid means the fluid which is sticky in nature. In that condition, the fluid will not flow from one region to higher region because it is very sticky in nature. So the permeability very less in that condition. Next, shape of the particles. Permeability is inversely proportional to the specific surface. Example, as angular soil have more specific surface area compared to the round soil, therefore the soil with angular particle is less permeable than the soil of rounded particles. Structure of a soil mass. For same void ratio, the permeability is more for the flocculent structure as compared to the dependent structure. As you can see in this picture you can easily see that the permeability is more in case of a flocculent structure and it is very less as compared to the dependent structure. Then the degree of saturation also affects the permeability. The permeability of a partially saturated soil is less than that of fully saturated soil. This one is partially saturated soil and this is fully saturated soil. It means only the water is present into the voids, and in partially saturated soil, air and water both are present into the voids. Okay, so in case of a saturated soil, the permeability is very more as compared to the partially saturated soil. Then the next factor is adsorbed water. Adsorbed water means it is a thin microscopic film coating which surrounding the individual soil grains particles. This water is not free to move and hence ultimately reduces the effective pore spaces and thus decreases the coefficient of permeability of a soil. If suppose the entrapped air and organic impurities are there, what will happen in that condition? Because of the presence of organic impurities and entrapped air, there is a obstruction between the flow, so the coefficient of permeability is reduced. Next factor is temperature. As the viscosity of the pore fluid decreases with the temperature, the permeability increases with the temperature. As the unit weight of a pore fluid does not change much with the change in temperature, as the temperature increases, in that condition the viscosity of a fluid will decrease. If the viscosity of a fluid will decrease, it means the fluid can flow easily from higher region to the lower energy region. In that case, we can say that the permeability of a soil will get increased. Stratification of a soil. Stratified soils are those soils which are formed by the layer upon the layer of the earth or the dust which deposited on each other. If the flow is parallel to the layer of the stratification, the permeability is maximum, while the flow in perpendicular direction occur with minimum permeability. Now the water flow, as we know, the water flow is divided into basically two categories. First one is laminar flow and the second one is turbulent flow. Laminar flow. Laminar flow indicates that each water particle follows a definite path and never crosses the path of another particle. It means in laminar flow, the water particles do not crosses each other path. They are following a distinct path. Likewise, as you can see in this picture, the particle follows a distinct path. So second is turbulent flow. In turbulent flow, the fluid particles follows a random path. They are following a random motion. They crosses each other path, and as you can see in this picture, the fluid particles follows in a zigzag way. They do not follow a distinct path. They are following a irregular or twisted movement. So the next topic is hydraulic gradient, which plays a very important role in permeability. When a water below a groundwater table surface is usually flowing under a hydraulic gradient defined as the slope of the free water surface in the direction of a flow. The hydraulic gradient is expressed as I. I is hydraulic gradient. What is hydraulic gradient? So as you can see in this picture, this is a soil specimen and this is the direction of a flow. Okay, water is flowing from one side to the another side, and these are the piezometer which are inserted to calculate the pressure head. So at point A there is a one piezometer which shows the pressure head, and at point B there is second piezometer. So this gives us what will be the head loss when the water is flowing from one side to the another side. So hydraulic gradient is nothing but it is the head loss divided by length of a specimen. Okay, so I will be equal to delta H divided by L, where I is nothing but hydraulic gradient, this delta H is nothing but the head loss, and this L is nothing but the distance between the point A and B. Darcy's law. Henry Darcy, he was a hydraulic engineer. His law is a foundation stone for several fields of study. Darcy's law demonstrated experimentally that for laminar flow condition in a saturated soil, the rate of a flow or the discharge per unit time is proportional to the hydraulic gradient. Darcy stated that the flow of a water through the porous media is directly proportional to the head loss and inversely proportional to the length of the flow path. This may be written as V is equal to K into hydraulic gradient. So we can write it as V is equal to K into I, where this K is nothing but the permeability coefficient or the hydraulic conductivity, and this V is nothing but the discharge velocity, or we can say that the average velocity. Discharge velocity, also called as average velocity, is the quantity of a total water which is flowing in unit time, where this Q is nothing but discharge through a unit gross sectional area, which is capital A, of a soil at a right angle to the direction of a flow. So the discharge velocity will be written as discharge per unit area divided by A. So the range of validity of Darcy's law. Darcy's type of flow is stable in character as long as the four basic conditions are always satisfied. So we can say that these are the assumption of Darcy's law. First assumption is the steady state is laminar flow. It means the flow should be laminar. 100% saturation should be there. It means there should not be any air. Flow fulfilling the continuity equation. No volume changes occur during or as the result of a flow. There will be no changes in the volume when the fluid will flow from higher energy to lower energy. Seepage velocity. The discharge velocity based on the gross sectional area of the soil. However, the actual velocity of a water, that is the seepage velocity through the void spaces, is greater than V. So a relation between the discharge velocity and the seepage velocity, if the quantity of a water which is flowing through the soil in a unit time is Q, then the equation will be write it as Q is equal to capital A into V, which is equal to A suffix V, V suffix S, where this Vs is nothing but the seepage velocity and AV is the area of a void in the cross section of the specimen. In permeability of a soil, we are considering the whole cross sectional area of a soil, rather in permeability we are considering the total cross sectional area of a soil, but in actual condition the water will flow only from the voids. But for a study point of view, we are taking the total cross sectional area of a soil. So an estimate of the actual velocity versus referred to as the seepage velocity can be made by considering the following equation, where this AV is equal to A suffix V into V suffix S. So the seepage velocity will be equal to AV by A into Vs. So this area we can write it as N. So V will be equal to N into Vs. So the permeability is also known as hydraulic conductivity. Hydraulic conductivity, marked as K, is one of the principal and the most important soil hydrology, hydraulic characteristics, or we can say that the parameter, and it is an important factor that is used in the water transport in the soil and is used in all the equation for the subsurface water flow. The value of hydraulic conductivity varies widely for a different soil. For the different types of a soil, the hydraulic conductivity will vary. The hydraulic conductivity of an unsaturated soil is lower and increases rapidly with the degree of saturation. The coefficient of permeability also varies with the temperature upon which the viscosity of a water depends. As I already told you, if the temperature is increases, in that condition the viscosity of a water will get decreased and ultimately the coefficient of permeability will increase. So the coefficient of permeability can also be represented by the equation. We are conducting the permeability test at a standard temperature, that is 20 degrees Celsius. So this is the standard equation for calculating the hydraulic conductivity, which is K20 is equal to Nt by N20 into Kt. So basically these are the typical values for the saturated soil, which gives the soil type and coefficient of permeability, which is in centimeter per second. If the soil type is clean gravel, in that condition the permeability will be 100 to 1.0. If the soil is coarse sand, in that condition permeability 1.0 to 0.01. And if the soil type is fine sand, in that condition permeability will be 0.01 to 0.001 centimeter per second. So likewise, based on the types of a soil, the permeability of a soil will also vary. The permeability is very less for clay, as you can see in this table. So basically we are having some empirical relation for calculating the permeability of a soil. Several empirical equations for estimating the value of a K, that is the permeability of a soil, have been proposed. Some of these, if the sand is uniform in nature, in that condition the permeability, which is in centimeter per second, calculated as C into D10 square, where this D10 is nothing but the effective size, effective diameter size in mm, where this C is nothing but a constant that varies from 1 to 1.5. For dense or compacted soil, in that condition the permeability of a soil will be calculated as 0.35 into D15 square. For medium to fine sand, in that condition the permeability will be calculated as 1.4 E square K 0.85, where this K is nothing but the hydraulic conductivity at a void ratio E, and this K 0.85 is the corresponding value at a void ratio of 0.85. So the hydraulic conductivity, that is K, is a measure of a soil permeability. The value of a K is determined in the lab using the two methods. Basically, these are the very important methods. First one is constant head permeability test, and the second one is falling head permeability test. As I already told you, the permeability of a soil plays a very important role in geotechnical engineering. So it is important to calculate the value of a permeability. So these are the lab tests. We can even calculate the permeability of a soil using the field method. In field method, there is a method which is pump in test. This method is performed in unconfined aquifer as well as in confined aquifer. So the value of a K is usually expressed in centimeter per second. The hydraulic conductivity is also known as coefficient of permeability. So in next class we will going to talk about how to calculate the permeability of a soil using constant head test and falling head test. Thank you.